Welcome to Koshika Training Institute. Let's start with VLSI flow. First, we do always RTL coding, followed by synthesis, and then followed with PD and STA. Now, since any manufacturing unit understands in terms of binary coding, we always start with statements. That is written using Verilog or VHDL, RTL coding. Then we convert it into a gate level representation using synthesis. But the real physical definitions under STA, all these features occurs during PD and STA stage. And then the GDS file is generated, which the tool, the manufacturing unit understands, and then it manufactures a chip. To identify if there is a functional fault or functional issues in the RTL or statements itself, we do verification. And to detect the manufacturing defects, we insert the DFT at the RTL stage and some features at the synthesis stage, and we do simulations after PD stage, and we also support on the real chip. This is the RTL flow. The ASIC flow starts with an HDL followed by RTL synthesis, then the netlist, and we optimize it, and we do the physical design and the layout. At any sort of stage, if there is no equivalence and if there is any fault, the whole process is repeated. And in the PD stage, we have placement, clock tree synthesis, signal routing, and finally the timing closure. Any sort of design will have metal, poly, tracks, substrates, pads, all these logics. We always have a Verilog code starting with module and a module name, ending with end module, each line ending with semicolon. The process of converting this code into the gate level representation is ASIC synthesis. To see the basic coding of MUX, we start with module, end module, module name, inputs, and if select is equal to 0, assign y is equal to a, else y is equal to b. That means when select is equal to 0, the output is selected, the MUX selects a path, and it selects b path when select is equal to 1. Similarly, if I want to write using the case statement, in this way, I can write the case statement with different cases like 0, 0, 0, 1, 1, 0, and 1, 1, and what line should be selected. This is an example of 4:1 MUX using case statement. Any sequential element will always be having always statement followed by positive edge clock or negative edge clock within the sensitivity list. And always block starts with begin and ends with end statement, and the module starts with module and ends with end module. Now when reset is equal to 1, we assign y less than or equal to 1 tick b0. And when that is not there, we assign q is equal to d. This is a d flip-flop without the reset pin. Now for the SPYGLASS tool, the SPYGLASS checks for LINT, CDC, RDC, and DFT. LINT, during SPYGLASS LINT, it checks for the RTL analysis, RTL statements which are non-synthesizable, RTL statements which may cause issues during synthesis, DFT, and STA stage. It identifies the RTL statements which are impacting the area, power, and delay. CDC to check if it impacts during the clock issues which may impact during DFT or STA stage, the reset domain crossing, and the DFT, which checks for the controllability at the top level and all the RTL connectivities, which may lead to scan DRCs. Now, if you see during synthesis, any sort of code is actually getting converted in terms of hardware. To understand what code gets converted into what sort of hardware after synthesis. Now, when we use always statements with sensitivity list having the enable signals or data signals, any such signals with only if statements, it infers a latch. When we have positive edge, the clock based sensitivity list with both if else statement, it infers a flip-flop. And if the same code without else statement or missing else statement may lead to latches. The case statement infers multiplexes. If the case statement does not have default statements, again that infers a latch. And if there is an improper way of defining the clocks or reset, the code may not be synthesizable. Example, over here, if I have pause edge clock or reset, where I am not mentioning whether it is a reset with pause edge or neg edge, this code may not be synthesizable. When you define both the positive edge or negative edge of clock and reset, the code will be synthesizable. This is the same example. And the inferring latch statement when you have missing default statements, and it infers a mux when you have default statement. When you have A, B, C or any normal signals instead of clock, it differs or infers a combinational logic. But if you have a clock based sensitivity list with the always block, it infers a sequential elements. See, within the brackets, here you don't have clock, here you have clock. This is your combinational logic, this is your sequential logic, which is flip-flop. Now, the best way to partitioning or synthesis is to combine the logics in such a way that the grouping is good and the timing issues are proper. And always consider the area as low as possible. The RTL guidelines for good synthesis for a clock is the clock should be global. It should not be gated clocks. We should avoid as much as possible the mixing of both positive and negative edge triggered flip-flops. And we should also avoid using internal gated clock signals. Now the guidelines for reset is we should always see whether it is a synchronous or asynchronous reset, whether it is an internal or external powered reset, or if it has more than one reset which is hard or soft. Now whenever it is asynchronous reset, it makes STA more difficult. And timing issues may come up, which may lead to simulation failures as well. The asynchronous reset is always hard to implement and does not require a free running clock. And automation is always more difficult. But synchronous resets is always easy to implement and requires a free running clock. How do you identify a synchronous and reset and asynchronous reset? And how do you code for it? If you mention only clock as a sensitivity list within the always set block, it becomes a synchronous reset. If you have both clock and reset with positive and negative mentioned within the sensitivity list, that is within the bracket, it becomes asynchronous reset. Now, instead of using hash symbol for a delay or trigger events, you can use nets and wires to create a delay, or you can create some dummy loops and dummy clock cycles to create a delay. Because these are non-synthesizable statements during synthesis. And triple equal to or not or double equal to is also non-synthesizable. The UDPs are non-synthesizable. The delay on built-in gates are non-synthesizable. The statements like real time, event, try 0, try 1 are non-synthesizable. But instead of it, you can use try symbol, wire WAN and all those things and supply signals. Instead of system task and real constants, you can use identifiers, sized constants, module task and function ports. Instead of force and release, you can use blocking and unblocking statements. Instead of fork and join, you can use KZ statements. And instead of initial, you can use always statements. Now, how do you launch the SPYGLASS tool and how do you verify the SPYGLASS LINT, SPYGLASS CDC and SPYGLASS DFT? To launch a SPYGLASS tool, once you provide with the license, we launch the tool with SPYGLASS piece ampersand symbol so that it launches the tool. Now in the tool, when you go for help and SPYGLASS manuals, using SPYGLASS, you can go with multiple SPYGLASS manuals and understand the rules. To create a new project, click on File and click on New Project and then save the project which is needed. Now if you want to add the files, that is, it can load both Verilog and VHDL. Click on Add Files, Add Design Files and select the design files and click on Add and OK so that you add your Verilog files or the design files for your SPYGLASS tool. Now once that is done, you have to read the design, clicking on Run Design Read. Then if there is any sort of errors, it pops up in the message window. Any such syntax error will be reported and we need to debug the RTL coding in terms of Verilog or VHDL. Now any sort of goal to be set, whether it is LINT or SPYGLASS, DFT or SPYGLASS CDC, you select the goals, clicking on the goal setup and select the rule you want to test it, and just run the selected code. Now for the advanced lint, if you have any sort of errors on the used inferred clocks, you should not use such, or if you're using it, you have to change the parameters or settings, making the use inferred clocks to be yes. Now once you have different goals to be run, you have the DRCs and you can verify it. For SPYGLASS, always we do at the block level, fix all the LINT, CDC and DFT, SPYGLASS DFT issues, modify the RTL coding, get the changes done, and at the top level, that is at the SOC level, we integrate all the blocks. To start with SPYGLASS LINT, we have SPYGLASS LINT rules which checks and reports the errors, if any present. Example, the array, case, reset clock, set, functions, latches, synthesis expression, simulations, events, loops, and lab rules. Now, the main commonly occurring lint rules are W18, 19, 69, 110, 111, 123, 336, 391, 392, 414, and 448. The W18 is for missing else statement and which infers a latch. W19 is for truncation of extra bits. W69 is for all possible case and default statements which should be present. W110 checks if the module instantiation and the port connections width doesn't match to the port width definitions. W111 checks if not all the elements in the array are read. W123 checks if all the identified signals and variables are read but not set. W333 checks for blocking statements which should not be present in sequential statements. W391 checks for if both positive and negative edge clocks are used. 392 checks for both positive and negative edge resets are used. And 414 checks for non-blocking statements which are used in combinational statements. And 448 used for both synchronous and asynchronous resets. Now this is the code where because of the missing else statement, if you see there is no else statement, that's why it reports W18. In this code, the queue is declared as 1 bit, but you are defining it as 4 bit. So it only uses first bit and ignores the next 3 bits or the truncates the next 3 bit. That's why it is W19, which is truncation of extra bits. Now, if there is no possible cases of all the case statements, example here default statement is missing, then it reports W69. If not all elements in the array are read, it reports W111. Example, here A is 3-bit declared, but at the output you are using only 2 bits. So the A of 2, that is 1-bit array you are not at all using, then it reports W111, which may lead to area wastage and it may also lead to synthesis issue due to floating gates, and it also leads to coverage issue during DFT. Now, any sort of signals which are defined but not declared or initialized is reported by W123. Example over here, net has been used, but when you see there is no declaration of net, you will get a value for A because it is an input. You will be able to observe the value of C because it is an output. But what is the value of net? It is not initialized, so it will be an X. So these kind of scenarios may lead to simulation failures or floating nets, and also may lead to coverage loss. So which we can identify early in the stage of the RTL, and that can be identified and fixed using W123 violation. Now, if there is a blocking statement, it should not be used in a sequential blocks. Is equal to represents a blocking statement. Because it is a clock based sensitivity list, which is within the always, it is a sequential code. And hence it is a sequential code. It should not have blocking statements here, which should be changed to non-blocking. Now we should not use both positive and negative edge clocks. If you're using both the positive and negative edge triggered clocks, you will have positive and negative edge flip-flops, which will lead to DFT issues. Always you have to use negative edge flip-flops at the insertion stage at the initial level and then the positive edge. So it may also lead to coverage losses and simulation issues, mainly the simulation issues. Usage of both positive and negative edge triggered reset or set. Such kind of scenarios may lead to coverage loss and also simulation issues. So that we will be fixing the code at the RTL level, and that is reported by W392 from SPYGLASS LINT. The non-blocking statement should not be used in the combinational block, and that is reported by W440. You should not use both synchronous and asynchronous reset or set signals, which is reported by W448. Now, to understand SPYGLASS DFT, let's understand what is DFT. DFT stands for Design for Testability. It checks if there is a manufacturing defect and if there is any sort of shorts or opens within that manufacturing of an IC, like short between a metal and ground, short between poly, all these scenarios. You check the IC on a real tester and check whether it is pass or fail. The controllability and observability are the pillars of a DFT. Controllability in the sense, at any point of node, you are able to provide the input or the value which you require to test the fault. Example over here, using the mux with the control point and the control enable 1, you are providing the value with the control point. Observability means you are able to observe the status of any node at the output port. So to observe here, the node A is observed via non-functional observation flop. The process of converting the normal flip-flop into scan flip-flop is called as scan insertion. Now, when the real design is converted into scan insertion, you have functional path, which is selected when scan enable is equal to 0 and the SI path when scan enable is equal to 1. You shift the data from input to output of each flop with scan enable is equal to 1. You capture the data when scan enable is equal to low. That is, it selects the D path. That is shift in, capture and shift out. Consider I want to detect the fault of NOT gate which is present over here. Now I want to detect stuck at 1 at the input of NOT gate. That means I need to provide value 0. That value I'll be able to provide by making SA is equal to 0. After one clock cycle, that values go to the NOT gate input. But now to capture what is the status of the NOT gate, whether it is faulty or not faulty, that value to be captured. To capture that data, you have to capture it using D path. To capture it during D path, you have to make SC is equal to 0. That is, scan enable low will make the capture path. Once that is done, you have to shift out so that it reaches the output port. For that, you have to shift in out. That is why shift in, capture, shift out. Shift mode will be like a pipe. From scan in to scan out, you will shift out the data. To understand the capture, let's take an AND gate. And if you want to test this node, using the flip-flop SI pin, you will be able to provide a value. And to capture this data, make scan enable low so that this data is captured and passed. To understand both shift and capture, let's take, suppose if we want to observe the fault of this AND gate, I will shift the values until the values reaches this AND gate, the input of this AND gate, so that I activate the fault. Then I capture the data of this AND gate, and then I need to shift out by 2 clock cycles so that it reaches the output port. Now what DFT DRC is, which is identified by SPYGLASS? The clock DRC, if there is any RTL connectivity, set and reset, and latches which impact the simulations and coverage. For the SPYGLASS stage, LINT CDC and SPYGLASS DFT catches most of the errors early at the RTL stage and reduces the issues at the DFT and STA or PD level. Example, the clock DRC, the reset DRC, the set DRC, the latch issues, the feedback loops, the tri-state and bidirectional pins. How is the impact of RTL SPYGLASS on DFT and STA? Let's see the LINT errors and the impact on DFT. The WI18 violation occurs if there is a inferring latch due to missing else statement. Now, when you have a latch, you are not able to control and hence you are losing some coverage. When it comes to W19, because of the truncation of extra bits, you have floating instances during the post-synthesis stage, which may lead to coverage and simulation issues. Now, W69, where all possible case and default statements should be present, it may lead to latches and lead to coverage loss or controllability issues. Now W110 is the module instantiation or the port connection width which doesn't match to the port definitions. then there will be a lot of floating instances post synthesis. Again, it leads to coverage and simulation issues. If there is not all the elements in an array are read and you are declaring multiple array, example, 4 arrays you are declaring, only 3 are using, fourth array bit you are not at all using. So since you have declared or defined an additional memory element, it takes some area which will impact during PD stage, makes it hard for PD closure. It may lead to timing issues and hence the simulation issues as well. Now, what if there are signals and variables which are read but not set? Such scenarios, some instances are floating. If you have a floating instance, there is no value. When there is no value, it will lead to X sources, which will lead to simulation mismatches. Suppose if this issue is reported to synthesis team when it checks, it will be due to the RTL level. So then the RTL guy should modify it. Then he should give that modified RTL to the synthesis guy, and the synthesis guy should synthesize and give a netlist to the DFT, and again the DFT engineer should work on it. So it is a repetition of process. To avoid such issues, we can fix these issues at the RTL level itself. Now, blocking statements should not be used in sequential elements, which will lead to coverage and simulation issues. And also, we should not use mix of both positive and negative edge triggered clocks. If you use mix of both positive and negative edge triggered clocks, it will lead to both positive and negative edge triggered flip flops. Then usage of both positive and negative edge flip flops will lead to simulation failures because of wrong data capture. So, and also to avoid such issues, we need to place negative flip flops at the initial level and then the positive flip flops followed by it. Usage of both positive and negative edge reset may also lead to coverage loss on the reset pins and also STA issues. Then again, the usage of both synchronous and asynchronous resets will also lead to coverage loss on the reset pins. Now to check if there is no scan DRC, but still you are facing simulation mismatches due to the wrong clock path. The wrong path connections is due to some RTL issue where the connection is wrong and the clock selected itself is wrong or the TDR selected itself is wrong. That scenario, even though you don't have a scan DRC, because of the wrong clocks which are reaching the flip flops, you will have simulation failure. Reset set and DRC example. If we see such example here, just because of the wrong connectivity or just because of the wrong data, you may get reset DRCs. Example, consider instead of mux select line getting connected to TDR5, which is always 0, it is getting connected to TDR21, which is always 1. Because of that, the mux line selects the combo logic which goes to the test mode of an OR gate, and hence you have a reset DRC. Just because of the wrong select line connection to the TDR bit. Now, how do you know which TDR bit value is what and how the connection should be? Always, the RTL guys will have the design documents which is intended for, and according to the design documents and the waveforms, we need to debug and modify the RTL coding. If there is any latch sources in the SPYGLASS, it will lead to X sources, which will lead to coverage loss. And if there is a flip-flop instead of a latch, it will give you good coverage. Now, what if there is a clock domain crossing? Because of the clock domain crossing, if there are two clocks, clock 1, clock 2, input is D, outputs are Q1 and Q2, and for second flip-flop, Q1 acts as an input as well. Suppose the clock 2 is coming earlier to clock 1, sorry, Q1, then it is a setup violation. and hence that may lead to metastable state or X or 0 or 1, any mismatch in the data, which may lead to timing simulation failure at the DFT stage. The solution for it is, does this issue can be resolved at a DFT stage or STS stage? The only possible solutions for this which a DFT engineer can fix is, if the clocks are synchronous or in phase and it is a single bit data, then lockup latches can be added. But what if it is not in phase and it is not single bit data? For a single bit data and not in phase, we can use a two flip-flop synchronization methodologies. But code modification doesn't help. The tool will understand and fix this issue only if you are using a library which is having two flip-flop sync lib. Now for multi-bit data, the CD solution would be FIFO to be used for multi-bit data synchronization, handshake and acknowledgement based clocks if the clocks are out of phase, and multi-bit. Now all this solution exists only by RTL methodologies. You need to modify the code, add this code within your main design to resolve the CDC issues. Got an idea why we need SPYGLASS CDC early in the stage? Because some of the issues we can only resolve at the RTL level. The advantage is we will reduce the multiple iterations. If we go to SPYGLASS DFT, the main goal of SPYGLASS DFT is to identify the clock level violations. That is, the all clocks should be controlled at the shift mode and it should be a test clock. Async 07 where async set and reset should be inactive during shift. Async 08 where async set and reset should be completely controllable during capture. The latch 08, all latches other than retiming latches must be transparent in capture mode. To solve the DRCs, we need to add waivers and constraints to SPYGLASS GUI. If still the DRCs are not resolved, you need to trace back in graphical interface, report it to the RTL team for what kind of clock or reset issue exists and get the RTL modified. Or if you are the sole owner of the block, modify your RTL design such that this DRCs are clean. To understand the clock level issue, let's take an example where for an AND gate one input is clock, but the other input enable, if it is not passed, the clock doesn't pass to the flip-flop, which is a scan DRC. To resolve such issues, you will add a constraint. Now similarly for the reset, you define the constraints. That is, to make the reset in an inactive state, you have to make A and B 1 so that the AND gate is 1 and the inverter output is 0 so that the clear is deactivated. Similarly over here, if you make reset to be 1, your clear pin is deactivated state. Example of the SPYGLASS design constraint file which is added is, first you define the current design where you mention the design top level module. Then you define what kind of clocks, whether it is a test clock, what value it is, that is the clock formats like return to 0 format, non-return to 0 format, that is the clock waveform formats. Then test mode, because reset value should be 1 so that the clear is deactivated and the reset is deactivated. As it is a test mode pin, you are declaring it as test mode with what name and what value. Because it should exist only during shift and you are able to get more coverage during capture, you are declaring it as a constraint for shift mode only. Now to waive any sort of violations, you can use command like waive minus rule, and whatever violations you want to waive it, you can add it over here. The inputs for SPYGLASS is SJDC file, that is SPYGLASS design constraint file, and waiver file, that is SPYGLASS waiver file, SWL file. Then you compile and report the DRC and fix it. The reports are DRC count, fault coverage, flop ratios, rule complaints, and non-scan informations. The impact is you can identify the issues early in the RTL stage and fix it, which will reduce the issues like DFT, scan DRCs, and simulation issues and ST issues, and coverage loss as well. Now, impact of RTL on STA is latches make difficult to fix the STA, mix edge of pause edge and neg edge clocks and resets, and CDC and RDC. Suppose SPYGLASS exists within the design and still the DRC errors exist at the DFT or STS stage. What scenarios this may exist? If SPYGLASS is not all involved in the flow, if there is some constraints of SDDC which is missed out by scan insertion team, then also the issue may exist. If there is automation in the company which may resolve only 90% of the issue, but still 10% of the issues is not resolved because that is design specific and it is not automated, then also some issues exist. If there are any different RTL versions and subversions which we are working on, then the issues exist. If the SPYGLASS and RTL team knows the issues will be resolved in upcoming RTL releases and it is ignored during RTL or SPYGLASS stage, then the DFT issues still exist. To understand with synthesis, the synthesis goes with three main steps. That is translation, optimization, and mapping. During translation, the code is converted into hardware or the gate level representation internally. After that, it will optimize the gate level structure into minimized hardware. Then it will map to the technology specific or the target specific libraries. The synthesis flow has RTL source constraints and technology libraries as input, and it provides the gate level netlist. The simplest synthesis command is you open the tool with DC_shell, you read the RTL coding with the RTL read_verilog command, you set the top level module with current design, you specify the clock, period, waveform, and the clock definition with create clock, minus period, and waveforms. You check the design, unicify and compile where your translate, optimization, and mapping occurs, and then you write out the netlist. To understand the flow through design compiler, in the synopsis dc.setup, we provide with the libraries, the target library, link library, and the synthesis library. We resolve the lab and compile issues. Like example, in the called instantiations, if we don't have any ports, that may throw error. If there is missing semicolon, it will show the error on the next line. Example, line 1, there is missing semicolon, it will report at line 2. Then with respect to the area, power, and delay, it starts the synthesis process. Example, if the synthesis given with area as the constraint, one simplest example to understand is instead of generic two input AND gates, you can use a technology specific 3-input AND gate, which will reduce the area. Similarly, with respect to timing, the optimization varies. With respect to power, again the optimization varies, where the maximum fan out, capacitance, the slope, everything is considered. Now the additional main topic to consider is there are two ways to reduce the power. One is by coding methodologies you will be able to reduce the power. The other main hardware based methodology is providing the clock gating circuitry or clock gating structure, which will reduce the dynamic power. Some logics which are not activated for the complete cycle should be gated with clocks to reduce the dynamic power. The clock gating structures of two kinds. One is latch based and latch free based. Latch free based is a single AND gate with enable and clock. Only when enable is passed, the clock will be passed and gated clock will be activated. But the industry standard methodology is the ICG structure or the CCG structure, that is integrated clock circuitry or clock control gating structure, where your internal logic is an AND gate with one input as clock, the other input coming from a latch, where the enable is latched. And this gated clock goes to the flip-flops.